So far, we've been talking about the potential or the voltage of electrical cells, but we should also talk about the capacity of a cell. And this relates to the current that we could get out of a particular battery or so-called battery capacity. At some point, we will use up all of the reagents inside of our battery and it will die. Well, how do we determine how quickly that can happen or what the battery can do? Well, we use a unit called an ampere, and an ampere is equal to 1 coulomb per second. So it's a rate based unit. This is called current. Current is measured in ampere, or you might have heard it called amps. So 1 ampere is equal to 1 coulomb per second. So how does this help us? Well, a lot of times we may say we can measure the current of something and we time how long that current has been generated. We can relate that back to how many coulombs. And then we could also use Faraday's constant to relate the number of coulombs that we have to the number of moles of electrons. And then once we have the number of moles of electrons, we can determine the number of moles of whatever other substance we have using our stoichiometry. So let's do a quick example about that. There are some batteries that are based off of zinc and they oxidize with the air. And let's just examine this reaction. We have a zinc battery. It's reacting with the air, and to make things simple, I'm just going to say 1/2 O2. Goes to a zinc oxide. This is a solid, and here's a gas. So this oxygen, generally when you're talking about the battery, comes from the air. And let's say that we're able to generate a current of a 0.2 amps for 9 hours. Now, the question is, what is the minimum amount of zinc that would be required to make this happen? I say minimum because our calculation is going to assume that the reaction is 100% efficient. And that's really not the case. We'll have to have a little bit more zinc in there to generate this current for that long, just because not everything is 100% efficient. And you'll also notice that if you increase the amount of current that you're drawing from a battery, it will die disproportionately faster than if you're drawing a smaller current. And this just has to do with how quickly you're operating on the electrodes. So you might rapidly increase the temperature as the reaction is going, which could artificially damage the battery, and you won't be necessarily getting as much capacity out of it. But in this case, let's just see how much it would take for this. So, amps is actually a conversion factor. And if you recall, usually when we're doing dimensional analysis, it's a good idea to start with the quantity that is not a conversion factor. This is just 9 hours. It's not 9 hours per something, it's just 9 hours. This, amps, is coulombs per second. So it's a conversion factor between time and coulombs. So we're going to start with the 9 hours here. Now, I know that amps is coulombs per second, so I'm going to need to convert hours into seconds. So let's do that. If you recall how to do dimensional analysis, it might have been a little while. There are 3,600 seconds in 1 hour. If you didn't want to do it this way, you could do 60 minutes and then 60 seconds, and that would be the same thing. And then let's use our amps to convert into coulombs. So I have 0.2 coulombs for every second. So now I'm in coulombs, a unit of charge. And now I'm going to convert the number of coulombs that I have into moles of electrons. To do that, I'm going to need Faraday's constant. Now, I want 1 mole of electrons up here, and Faraday's constant is 96,485 coulombs for every mole. So, if I do this out, I will get the number of moles of electrons that I need to generate this current for that long. I could have continued on with the dimensional analysis, but sometimes people like if I stop halfway there. So now I have the number of moles of electrons. Now I need to convert to grams of zinc. Now, I'm going to need to know how many electrons I use for every zinc. So we'll have to look here and see, well, this is zinc 0, so I went from 0. Now I need to determine what the charge is over here, or the oxidation number. Now, if you remember back to the rules, oxygen is always -2. And so, since this is a neutral compound, zinc must be +2. And that is the typical ion for zinc. So, we should know that we gave up 2 electrons to get to this +2. So it takes 2 electrons for every zinc. So we'll use that in our conversion factor here. So we need this many moles of electrons. Let's convert into moles of zinc. And remember, since we went from 0 to +2, that's 2 moles of electrons. And then, since we need to know the mass, we'll just use the molar mass of zinc, which is 65.38. And I get about 2.20 grams of zinc. And that's how to use the Ampere to do some calculations to determine what the battery capacity is. And this is also something that you can do to determine how much of a substance would you need to get a certain amount of capacity. And a lot of times people think, wow, we're really advancing battery technology, and we are, but there will be a fundamental limit to how dense a battery can be, or how small it could be for a given amount of energy, because there's fundamentally a limit on how much you'll need to generate that. And keep in mind that this is not the only component to the battery. We'll also need porous membranes to separate the reactants from each other so that the battery doesn't short out. And we'll need some structure to it, and electrodes, and the list goes on. So a lot of times the actual mass of the substances inside the battery is only maybe 10 to 30% of the mass of the battery. And the rest of it is the structure and the electrodes and all of the other pieces that are required to make those reactions actually useful to us. But this will let you calculate at least the minimum quantity of reactants required for an electrochemical reaction.